Welcome to the deep dive. So today we're really plunging into this challenge that keeps, the most advanced machine learning folks kind of scratching their heads.
Yeah, how do you build a system that gets uncertainty? Not just like a margin of error.
Right, not just a blurry number, but like a whole landscape
Yeah.
with maybe multiple different answers.
Exactly. Multiple distinct solutions. And our mission today, well, it's to give you a shortcut to understanding something called the Schrödinger neural network, the SNN.
Okay, SNN.
Yeah, it's a really novel approach. It tackles this whole multimodal uncertainty thing by basically borrowing the language of quantum mechanics.
Quantum mechanics. Okay, let's unpack that. So for you listening, the central problem here is about robustness, right?
Absolutely. If your input data is ambiguous, and that happens all the time, like in inverse problems or complex modeling.
Then the output isn't just one thing. It's inherently multi-valued.
Precisely. And standard methods, while they're usually trained for average performance, they just completely fail to capture that complexity.
They just mush it all together.
Yeah, forcing multiple possibilities into a single, often pretty useless average prediction.
Hmm.
So to make good, risk-aware decisions, you need the full picture, the conditional probability distribution, PX stars.
But you're saying existing techniques struggle with that.
Right.
When it's not just a nice, simple bell curve.
They choke, especially when that distribution gets weird, non-Gaussian, heavily skewed, or the trickiest one, multimodal, having multiple peaks.
Yeah.
And this is where the SNN comes in. It fundamentally reorients the problem. Instead of predicting, say, a probability density directly,
It predicts something else.
it predicts a complex, normalized wave function. And this thing is defined over the entire output domain, high dollars.
Okay, hold on. A wave function. So if I'm getting this right, the core idea is we're shifting. We're going from predicting just a few numbers about the output to predicting an entire field or like a shape that encodes all possible outcomes rigorously. Is that the amplitude first learning idea?
That is absolutely the core concept. But, to really appreciate why the SNN is so elegant, we kind of need to feel the pain first.
Feel the pain. Okay.
Yeah.
You mean the limitations of what we currently use.
Exactly. We need to understand the frustration with the current big players in uncertainty quantification, or UQ.
All right. Where do we start? Mixture density networks. MDNs. They seem like the most obvious fix for multimodality, right? Just stack a bunch of simple distributions.
Yeah, usually Gaussians, they try, they really do, but honestly, they hit an architectural wall pretty fast.
How so?
Well, the first big headache is what you could call component bookkeeping. You, the designer, have to guess up front how many components, how many Gaussians you need. Let's call that number in dollars.
And if you guess wrong?
If you pick too few, you can't capture the complexity you underfit. If you pick too many, oh boy, training becomes incredibly brittle. Really unstable.
What kind of instabilities are we talking about?
You get things like label switching. Component 1 might suddenly decide it's component 2 halfway through training, just randomly swapping identities between batches.
Ah, okay. That sounds messy.
It is. And then there's degeneracy, where multiple components might just collapse onto the same spot, predicting the same mean, so you're basically wasting capacity.
Right. Makes training very sensitive, I imagine. Very finicky.
Super finicky. Okay, so if MDNs are maybe too unstable, then people often turn to normalizing flows, NFs.
Yeah, NFs are popular. They're known for being expressive. And crucially, they give you an exact likelihood. You know exactly how well your model fits the data.
That exact likelihood is their superpower, but it's also their cage. To get it, they must use invertible transformations, and the Jacobian determinant of those transformations has to be easy to compute.
That sounds restrictive.
It is restrictive. It's like an architectural prison. If you want to capture really sharp, separated modes, like those two distinct possibilities we talked about earlier,
Yeah.
you're forced to build these incredibly deep, complex network architectures, often very slow to train. The engineering overhead is huge because that invertibility requirement really limits your design choices.
Okay, so MBNs are fiddly, NFs are restrictive. What about energy-based models? EBMs. They seem the most flexible, conceptually. No invertible layers, no fixed components.
They are very flexible, but they come with their own monster problem. The partition function.
Ah, the normalizer. Z theta, the thing you need to divide by to make the energy into a proper probability.
Exactly. And in continuous spaces, that integral needed to calculate Z theta is almost always intractable. You just can't compute it analytically.
So you can't get an exact probability. How do you train them then?
You have to sample, usually with computationally intensive methods like MCMC, Markov chain Monte Carlo.
Which is slow.
Yeah.
And resource heavy.
Very slow, very resource heavy, and prone to bias from the sampler itself. So you might get a really nice flexible density shape in the end, but you've given up the ability to calculate exact likelihoods efficiently.
And the training time can make them impractical for a lot of real-world uses.
Totally. So there's this gap, right? The field desperately needs a method that's expressive enough for multimodality, but still keeps things analytically tractable.
And this is where the SNN makes its quantum leap, borrowing from physics. How do we even justify bringing quantum mechanics into machine learning?
Well, it's not arbitrary. It really rests on two key pillars, ideas from physics that are about a century old now. The first is de Broglie's association.
Okay.
Remember how de Broglie associated a wave with a particle? The SNN does something analogous. It associates a complex amplitude field, this wave function, with each input data case $6, and this field exists over the whole output domain.
So it treats the uncertainty itself as a kind of wave object.
Precisely. It's a conceptual license, but a powerful one.
And the second pillar, how do we get from this abstract ways to a prediction we can actually use?
That's Born's rule. It gives us the operational meaning. The probability density we care about, you get it by taking the squared modulus of the wave function. So 5 $2 is proportional to 2.
So squaring the complex amplitude gives you the real valued probability.
Exactly. The amplitude itself is complex, but the observable probability is real and non-negative, just like it should be.
Okay, but you mentioned the partition function nightmare for EBMs. If the SNN needs normalization too, because the SNN needs integrate to 1, how does it avoid that same trap? You said analytic normalization. That sounds almost too good.
It sounds too good, but it's down to a clever choice of representation. It's structural. The SNN doesn't just use any function for ESLink. It expands the wave function using an orthonormal spectral basis, usually Chebyshev polynomials.
Orthonormal basis. Why is that the key?
Think about vector math. If you have basis vectors that are orthogonal in unit length, calculating the squared length of any vector is easy, right? It's just the sum of the squares of its components, Pythagoras' theorem. It's the same idea here, but with functions. Because the basis functions are orthonormal, the integral of the squared magnitude of the wave function, which is the normalization constant, simplifies dramatically. It just becomes the sum of the squared magnitudes of the expansion coefficients.
So calculating that nasty integral collapses into a simple algebraic sum.
Exactly. You turn a potentially intractable numerical integration into a simple 2 norm calculation on the coefficients the network outputs.
Wow. Okay, that is a game changer for speed, for stability.
Absolutely. Normalization is achieved just by projecting the network's output coefficients onto a unit sphere. No MCMC needed, no complex integration. It's baked into the structure.
All right, so normalization is handled. Now, how does the multimodality appear? If we're not explicitly putting in Gaussian blobs like MDNs, where do the multiple peaks come from?
They emerge naturally from interference. It's the magic that happens when you square the complex amplitude.
Interference, like waves canceling out or adding up.
Precisely like that. Think about sound waves or water waves. If two wave crests meet, they reinforce each other. That's constructive interference, creating a bigger peak. In our case, a high probability region.
Okay.
If a crest meets a trough, they cancel out destructive interference. That creates a flat spot or silence. In our case, a deep valley of low probability between peaks.
So the peaks and valleys in the probability distribution are sculpted by how these complex basis modes add up and subtract when you calculate too.
You got it. The cross terms that appear when you square the expansion are crucial. Multimodality and asymmetry aren't forced. They emerge from these interference patterns.
Which brings us to the network itself. Its job isn't to predict an ETAC directly.
No. Its job is to predict the complex coefficients of that spectral expansion of 2.
So the output is a set of complex numbers, multiple tachy plus I BK2.
Correct. And this is really important. The fact that they are complex is not just some mathematical quirk, it's essential.
Why? If the final probability Py is real, why complicate things with imaginary numbers in the middle? What does that EBK dominant actually do for us?
It gives us control over phase. Think about it. For a fixed number of basis functions, let's say color, using complex coefficients, AK plus IBK doll, instead of just real ones, essentially doubles the number of parameters the network outputs.
Okay, so more parameters, more flexibility.
It's more than just raw flexibility. It gives us additional phase degrees of freedom. The total probability mass, the Tolatu norm sum CP22, doesn't depend on these phases. It stays constant.
Right, because A plus IB2 equals A2 plus B22. The phase angle cancels out in the magnitude.
Exactly. The relative phases between different components, like the phase difference between SUT-Deller and SE2, critically erect those interference terms when we calculate 6p equals some ATLC2.
So the phases act like dials to control the constructive and destructive interference pattern?
Precisely. They are the fine-tuning mechanism for the shape of the probability density, independent of its total magnitude, which is fixed at 1 after normalization.
That's incredibly efficient. You can sculpt sharp peaks, deep valleys, make the distribution skewed, all by tweaking these phases without necessarily needing a huge number of basis functions of dollars.
That's the parsimony. And the papers show this clearly. They compare the complex SNN, CSNN, with a hypothetical real SNN, RSNN, that only uses real coefficients.
And the difference?
The RSNN, lacking phase control, struggles. It either smooths things out too much, filling in the low density valleys between modes, or it needs a much larger basis size dollars to try and approximate the same sharp features that the CSNN gets easily via phase interference.
Fascinating. So the imaginary part is doing the heavy lifting for shaping the final real probability. Okay, moving on. There's a third quantum concept you mentioned, the operator postulate. This gives us a way to query the model.
Yes, and it elevates the SNN beyond just being a density estimator. It turns it into like a full physics engine for handling uncertainty. The idea is that any measurable quantity you might care about, the mean, the variance, the probability of exceeding some threshold, some complex risk metric, corresponds to a mathematical object called a self-adjoint operator. Let's call it a dollar.
Okay, and the SNN lets us calculate the expected value of $I.
Exactly. The predicted value of that observable, given input $6, is the quantum mechanical expectation value, written as a Langle-Schrangle.
That looks potentially complicated. Why is this efficient for a data scientist?
Again, the magic is in the spectral basis. When you work it through, that expectation value calculation simplifies beautifully. It reduces to a simple, efficient, and fully differentiable Hermitian quadratic form involving the coefficients,
Meaning
it's just 6 FCX, where tesses is the conjugate transpose of the coefficient vector dollars, and $5 is a matrix that you can pre-compute based only on the operator 8a and the chosen basis functions.
So calculating the mean or the variance or some risk measure boils down to just a matrix multiplication with the coefficients the network already produced.
Pretty much. You turn what looks like a complex integral into something computationally cheap, instantaneous, and crucially differentiable. You can backpropagate through observable calculations.
That efficiency is huge.
Sure.
And this operative view also helps with regularization. The papers talk about physics-inspired knobs for training.
Right. We get two really useful quadratic regularizers that act as transparent controls over the shape of the final density. The first is the kinetic energy penalty.
Kinetic energy. Sounds like movement.
Sort of. It penalizes the first derivative of the wave function with respect to the output variable, so partially great. In simpler terms, it penalizes roughness or high-frequency wiggles in the wave function, which translates to penalizing sharp peaks or rapid changes in the probability density.
So cranking up the kinetic energy penalty smooths out the prediction.
Exactly. It's an explicit knob for controlling smoothness. And interestingly, there's a Heisenberg-like trade-off baked in. If you force smoothness by penalizing each chain, you necessarily broaden the peaks. You increase localization in momentum frequency space, which increases uncertainty in position space.
Okay, that makes sense. What's the second knob?
The potential energy penalty, EPOT. This one uses a shaping function, VT-jaw that you choose, to basically guide where the probability mass prefers to concentrate.
How would you use that in practice? Give me an example.
Well, suppose you have some prior knowledge that the answer should probably be close to 0, but you don't want to force it absolutely. You could add a potential energy penalty using a simple quadratic, like VA equals Y22.
Like a gentle nudge towards the center.
Exactly. It creates a differentiable force, pulling the probability mass towards E-tellers without forbidding solutions far away if the data strongly supports them. So you get these two transparent controls. EB for smoothness spectral content and EPOT for spatial localization. It's a much cleaner way to manage the bias-variance trade-off.
All right, theory sounds good. Left-talk verification. The papers often use this classic test case, the noisy sine wave inverse problem. 6x equals t plus 0.3 Brini plus epsilon. Why is that such a good benchmark?
Because it's inherently multi-valued. The mapping from the latent variable 2 to the observation scalar is non-monotone. It goes up and down.
Meaning a single observed value of 6L could have come from multiple different true values of 2I.
Exactly. Sometimes 3 or even more possible 2's. A standard regression model trained to predict from $6 would just output the average of those possibilities, completely useless.
But the SNN?
The SNN shines here. When you train it to predict the distribution, PTXC, it successfully recovers the full multimodal posterior. You see these distinct ridges of high probability density tracking the different true branches of the solution. It demonstrates the SNN can handle that fundamental many-to-one ambiguity.
Okay, and because the output is multimodal, just checking the average likelihood isn't enough to know if it's doing a good job, right?
Right.
A model could get high likelihood by just being vaguely right everywhere.
Precisely. You need a more sophisticated evaluation framework, especially if you care about the structure of the uncertainty.
So the papers propose a multi-axis approach.
Yes, assessing performance across 3 critical aspects. First, mode count. Does the SNN actually find the correct number of distinct solutions or peaks? We call this error a count.
Makes sense. What's second?
Second, mode location allocatum. Okay, it found the right number of peaks, but are they in the right place? This is tricky because you have to match the predicted peaks to the ground truth peaks fairly, usually done with something like the Hungarian algorithm for a minimal cost assignment.
Right, so you compare predicted peak locations to the true ones. And the third axis, this seems crucial for real-world use.
It really is. It's mode mass allocation. This asks, is the total probability mass distributed correctly among the different true solutions?
So if one solution branch is genuinely twice as likely as another?
Does the SNN assign roughly twice the probability mass to the region around that first solution? We measure this using the total variation distance between the predicted mass in the Voronoi regions, defined by the true modes, and the actual ground truth mass distribution.
That sounds comprehensive. Count, location, and allocation. It ensures the SNN isn't just finding peaks, but correctly weighing the likelihood or risk associated with each distinct possibility.
Exactly. And the bottom line, the practical implication here, is that because you have the full density represented by these coefficients and you have the operator calculus,
You can calculate things like quantiles or expected shortfall or other risk metrics directly and analytically.
analytically and efficiently. No need for expensive post-hoc sampling. That's huge for applications in finance, robotics, safety critical systems, anywhere you need robust, risk-aware decisions.
So summing up the SNN's advantage, it seems to synthesize the best bits of previous methods while avoiding their main pitfalls.
I think that's fair. It gets the exact likelihood training, kind of like normalizing flows.
The ability to handle expressive multimodality, like MDNs were supposed to.
But delivers both with this unique analytic tractability, thanks to the quantum-inspired structure and the operator calculus. It really is a different way of thinking.
Okay, one last thing before we wrap up. Scaling. This spectral expansion using polynomials, doesn't that run into the curse of dimensionality? If your output Jollar is not just one number, but a vector in math theorem, does the number of coefficients explode?
That's a critical question. A naive tensor product expansion would explode exponentially. The solution is to use low-rank tensor approximations.
Like tensor trains or CP factorization.
Exactly. Things like canonical polyadic CP factorization allow you to represent the high-dimensional coefficient tensor using a number of parameters that scales only linearly with the output dimension dollars instead of exponentially.
And crucially, do these low-rank structures preserve the benefits, like analytic normalization?
Yes, that's the beauty of it. These structured tensor formats are designed to maintain properties like analytic normalization and closure under the operator calculus, even while drastically reducing the parameter count. So, the path to multivariate outputs is feasible.
This has really been a deep dive then, showing how borrowing structural rules from physics, from quantum mechanics, can fundamentally redefine how we handle uncertainty in machine learning.
It changes the basic unit of prediction, doesn't it? From predicting just a single number or maybe a mean and variance to predicting this entire conditional wave amplitude, which encodes everything.
And that really leads to a final, very provocative thought. Just like quantum mechanics forced physicists to shift their thinking away from definite particle trajectories and toward probability amplitudes, well, SNNs maybe suggest a similar shift for data scientists, elevating our goal from predicting simple statistics about a data point to defining a structured conditional wave that encodes all its possible outcomes and their likelihoods. It really reframes the problem. And it makes you wonder, if the structure of quantum mechanics proves so useful here, what other fundamental physics concepts are just waiting out there? thermodynamics, relativity. Could they hold keys to completely new ways of modeling data in structure in the future?
That's definitely something to think about. What unexpected connections are still waiting to be discovered?
Indeed. Plenty to chew on. Thanks for joining us on the Deep Dive.